Hi, everyone. So we've been talking about wave function. And first, I want to make clear what this notation means. When we talk about the wave function, psi is a function of x and t. So this is not like the coordinate of a, this is not x in the sense of the coordinate of a moving particle. This is the wave function as a function of space at the given time. So let's say at t1, maybe the wave function looks like this. So this is t1. And what is this good for? Well, if you take the square of the magnitude of this wave function, that gives you the probability density at all locations in space and all times t. So for example, at t1, if you square this thing, not square, if you compute the square of the magnitude of the wave function, it will give you the probability density, right? So it would look something like, maybe something like this. I'm drawing the real function because it's hard to draw the complex function, but it would be something like this, right? So this is psi squared. And how do we find the psi squared? Not psi squared, the square of the magnitude of psi. Remember how to do this? You take psi star and multiply by psi. This is really how to do this. At a later moment in time, the wave function will have changed. It evolves. You see, the wave function evolves in time. So perhaps this is some kind of a wave moving to the left, and maybe at a later time it will become something like this. So this is T2. It moves, it changes shape, it evolves. The wave function evolves. So again, x is not the same as x in classical mechanics. In classical mechanics, you describe the particle by specifying its coordinate as a function of time, x versus t. In quantum physics, you specify the wave function, which is defined at every point in space, and it evolves in time. And what's the wave function good for? Well, you can compute, for example, you can compute the probability distribution of where you would find the particle if you were to measure its coordinate. Turns out wave function contains other information, not just coordinate probabilities. It also contains information about energy probabilities, momentum probabilities, all kinds of statistical information is encoded in the wave function. So I just want to make sure that you understand what this notation means when we write something like this. In any case, so how does the wave function evolve? How, oh, why is this so thick? So question, how does psi evolve? What determines its evolution in time? And the answer is evolution of psi is determined by the Schrodinger's equation. I'm going to just abbreviate. Last week, we encountered a special case for a particle that's moving freely, not interacting with anything, free particle. We saw that a solution, I stated the Schrodinger's equation, and I readily showed that the solution to the Schrodinger's equation is a plane wave, but since principle of superposition applies to quantum mechanics, it could also be a superposition of plane waves, so we can build a wave packet. It will be some kind of a wave packet that evolves in time. So now we're going to go up one notch. I will tell you the Schrodinger's equation for a more general case when a particle is interacting with something. So let me first state this. I'm going to write this down in color. Let me write this down in color. It will look intimidating, but don't be afraid. We will digest this very slowly, step by step, and understand how to extract information from this equation that we need. That's basically the program for the rest of the quarter. So Schrodinger's equation reads like this. So this is I, complex number, root of -1, times h bar, times the time derivative of the wave function with respect to time is given, well, it's given by the following thing on the right-hand side. The spatial second derivative of the wave function. So far, it's exactly like what you saw last week. But in addition to this, what I just wrote so far is exactly what we had last week. But in addition to that, if the particle is interacting with something, there will be another term here, right? And I'm not specifying that wave function is a wave function of, it's a function of space and time. I don't always have to explicitly remind you that it's a function of space and time. It's implied. So what is this U? U is a potential energy. This is a potential energy. So when we study classical mechanics, when students are introduced to classical mechanics, like Phys 1, we think of interactions as represented by forces. Forces represent interaction. So here are two fists. They're interacting by means of force. This fist is applying the force on this and vice versa. We learn that there are two types of forces, conservative forces and non-conservative forces. For example, gravitational force is a conservative force, or electric force is a conservative force, or spring force is a conservative force. And then there are other things called non-conservative forces, for example, friction. Non-conservative forces don't have potential energies associated with them. It's a good thing for you to think about why. It's a really good way to quickly refresh on classical mechanics. But if a force is a conservative force, that force has a potential energy associated with it. So spring force has a spring potential energy, electric force has an electric potential energy, gravitational force has gravitational potential energy, and so on. And if you know potential energy, you can find the force. If you know the force, you can find potential energies. So interactions are encoded by forces, but equivalently, interactions are also encoded by potential energies. And in quantum mechanics, interactions are encoded by potential energies. We don't so much deal with forces, we deal with potential energies. In classical physics, there you can get the force if you know potential energy and vice versa. Quantum mechanics likes to deal with potential energies. So far, I wrote down the full Schrodinger's equation for a particle that's interacting with something by means of a potential energy. And for the rest of this lecture, I want to review some ideas from classical mechanics. So, question. In classical physics, how do you get forces forces from potential energy. This is a bare minimum. You absolutely have to know this. This is like this is the basics. It doesn't matter what you major in, electrical engineering, computer engineering, you have to know how to get forces from potential energies and vice versa. So answer in one dimension, in 1D, force is given by minus the derivative of potential energy with respect to space. Potential energy can be time dependent, but usually it's not, so it's just a regular derivative. So for example, let's take the spring example. Let's say you have a spring, and on the end of the spring there's a mass, and here's the equilibrium position, right? So this is, we call it x equals 0. And so the particle can be displaced to the right of the equilibrium or to the left of the equilibrium. If it's displaced to the right of the equilibrium, the spring is stretched. If it's displaced to the left of the equilibrium, the spring is compressed. So x is really displacement from equilibrium. And so it's convenient to set x equals 0 at the equilibrium point. I can, yeah, so I guess on the side I can say this is like a granddaddy problem. A more interesting, a related problem is two masses on a spring. Like, why would you care about that? This could be a model for a diatomic molecule. It turns out that while this is not the same as the mass on a spring attached to a wall, there's a very closely related problems. So by understanding this problem, we go a long way towards understanding this problem. Okay, so what I'm going to do now is I'm going to plot the force as a function of coordinate x. And you know what the force is, right? So F equals minus kx, also known as Hooke's law. I think there's an S on the end, right? Hooke's law. Let me erase this so it doesn't confuse you. F equals minus kx. Well, k is positive, so here's what this graph looks like. And the slope is minus k. So what this says is when x is positive, the force is negative. So the force is trying to push the mass towards the equilibrium. And when x is negative, the force is trying to restore the mass back to equilibrium as well. So this is a restoring force, right? Restoring force. So that's what this graph means. You also learned, so I'm going to continue, I'm going to graph the potential energy, and I'm going to line the graph. So oftentimes I ask you to draw graphs, and I ask you to align them. So there's some kind of a feature in the force, for example, some extremum or crossing 0. I want to see the corresponding location on the potential energy graph. So aligning graphs is something that we do a lot. So here's the potential energy. And you might remember that U equals 1/2 kx squared. You may have learned that. So, okay, so I'm going to draw this potential energy graph. So here's my parabola. Okay, so this is 1/2 kx squared. And so first I want to check du dx equals minus 1/2 times 2kx equals minus kx. So it checks out. This force is indeed the derivative of this potential energy. So you may think of this as just a divine inspiration, and you check it by taking the minus of the derivative, and you get, by taking the minus of the derivative, and you get the right force. Okay, so the force is minus the derivative of the potential energy. And if the force is minus derivative of the potential energy is minus the integral of the force. The potential energy is minus the integral of the force. So you can write this in two ways. You can write this as an indefinite integral. And then how do you determine the C? Well, the C is determined by some other additional information. So determine or fix C with additional information. We often call it boundary conditions. If I tell you the value of the potential energy on the boundary, that fixes the C. This is called boundary condition. You will see a lot of this term in the coming days. So this is method 1. And method 2 is, you could say that you can build the boundary conditions into the integral. You could say that this is method 2. It's minus, you can write it like this. Of course, if the upper limit is x, I cannot call the integration variable x. So I'm going to have to do something like this. This is called a reference point. And so you can see that potential energy valued at the reference point has to be 0, right? So u at x naught equals 0, because then you get x naught to x naught of whatever, that always results in 0. You're integrating over no range. So this is an example of so this is boundary condition. So this is an example of a boundary condition. So my boundary condition is that I set potential energy to be 0 at x naught. If I follow method 1, I have to first take the integral, and then I would have to find the C that ensures that potential energy is 0 at position x naught. Let's check. So check. So I'm going to check following method 1, u equals minus kx dx plus c. This is 1/2 kx squared plus c. And then if u at x equals 0 equals 0, in other words, if I choose to set potential energy to be 0 at the equilibrium point, then c equals 0. So when we say that u equals 1/2 kx squared, we imply that we define potential energy to be 0 at the equilibrium point. Notice I don't have to do that. I can set the potential energy to be 25 joules at the equilibrium point. Then C will be 25. Potential energy is defined up to a constant. You can always add any constant to a potential energy. Let me repeat this. Potential energy itself is defined only up to a constant. You can always add any arbitrary constant to a potential energy. It does not affect the physics. The force is still the same. The force is a derivative of potential energy. When you add a constant, it doesn't affect the force. So the push or pull that you feel is independent of what value you add to the potential energy. I could also do method 2. So this is, so I could also say that u equals minus between 0, that's my reference point, is 0 and x, minus kx prime dx prime, and I have 1/2 kx squared. So I get the same answer, right? Maybe I should put an intermediate step, kx prime between 0 and x, right? Which is 1/2 kx squared. So in both cases, u is defined with respect to some reference point. I can choose a different reference point, and if I choose a different reference point, that will add some constant to my potential energy. So u is defined respect to some reference point. You see, this is explicit method 2. A reference point is in the equation. So U is not unique. You can always add an arbitrary constant to U. Or you are free to choose a reference point. Potential energy is always 0 at the reference point. Again, you can see that explicitly. If x equals x naught, potential energy is 0. So back to the spring example, if I choose the reference point, not the equilibrium point, but some other point, it's at that other point the potential energy would be 0, but it would not be 0 at equilibrium point, which is equivalent to offsetting the potential energy by some constant. Okay, so what matters physically is not the value of the potential energy, but differences in potential energy. So if I have, difference in potential energy between point 1 and point 2 is given by equals minus the work done by force F in going from x1 to x2. Going back to the spring example, let's say this mass is moving from this point to this point. Does the spring force do positive work or negative work? It does. The spring force does positive work. So the change in potential energy is negative. The potential energy is decreasing. So delta U in going from this point to this point is negative. On the other hand, if you go from this point to this point in the other direction, the spring force is opposite to the direction of motion. So the spring does negative work. So delta U is positive. Potential energy increases. What does it mean to say that the spring does negative work or the spring does positive work? The spring does negative work means it's removing removing the kinetic energy from the particle. The particle's kinetic energy decreases. And when we say that spring does positive work, it adds the kinetic energy to the particle. That's from kinetic energy theorem. So we can see that as potential energy increases, kinetic energy decreases, and vice versa. I will explore that in the coming video. Actually, I will explore that in a moment. We will get to that point. Okay. The force F equals minus du dx is a conservative force. So the force in these integrals right here, it's a conservative force. And the reason it's called a conservative is because there is a quantity that's conserved. So, for example, spring force. Spring force. So this means that if only this force is acting on a particle, just the spring, there exists a quantity that's conserved. There exists a quantity that remains constant throughout that motion. What is that quantity? What is that quantity? That quantity is this interesting combination of velocity and position. You know this in classical mechanics as kinetic energy, and this we just defined as potential energy. And because it's a constant, so while velocity is changing and position is changing, there is this interesting quantity given by this combination that is not changing. And because it's not changing, it deserves a special name. It's called mechanical energy. So kinetic energy plus potential energy equals constant, and we call it total mechanical energy, or just mechanical energy. And we use letter E for energy. So we say that mechanical energy is conserved. It's constant from one instant of time to another. So back to the mass on a spring example, if I look at the potential energy function, so this is my coordinate, and this is my potential energy function. It's a parabola. I'll try to draw a beautiful parabola. Okay. Oh, this is good. And so here's a constant energy. So this is E. And while the potential energy is changing, the kinetic energy is also changing such that the sum is a constant. You can think of kinetic energy as being energy minus the potential energy. So if this is the potential energy, the remainder is kinetic energy. You see? So this is kinetic, and this is total energy minus the potential energy. At some other point, let's say right here, the potential energy has a different value, and the kinetic energy complements the potential energy so that the sum remains a constant. Another way to visualize that is by the following graph. So here's the coordinate. Here's this poor, can't get this right. It's very hard to draw a beautiful parabola. So this is the potential energy parabola. And so here's my total energy. And here is the kinetic energy. So you see when potential energy equals U, kinetic energy is 0, and you get, you know that the kinetic energy as a function of position would be something like that. So wherever the potential energy is 0, kinetic energy is maximum, and vice versa. So this is a brief review. This is supposed to be just a review of concepts from basically introductory physics, reviewing potential energy, kinetic energy, and conservative force. Not all forces are conservative. Friction force is not a conservative force. And so there is no such thing as friction potential energy. If you have a bunch of forces acting on a particle, some are conservative, some are non-conservative, you can define the total potential energy of the conservative forces. And what the non-conservative forces do is they make sure that the total energy, total kinetic energy plus, or kinetic energy plus the total potential energy is no longer constant. So for example, if you add friction to a mass on a spring, the oscillations of the mass die down. And what that means is that the total energy, total mechanical energy, spring potential energy plus the kinetic energy slowly decreases. So in the absence of non-conservative forces, the sum kinetic plus the spring potential energy is a constant. It doesn't change in time. But if you add non-conservative forces, then kinetic energy plus the spring potential energy will slowly decrease. You can also have situations where non-conservative forces actually increase the mechanical energy. Luckily, we will not be dealing with non-conservative forces. Fundamentally, all forces are conservative. And so when we do quantum mechanics in this class, we will be dealing with conservative forces, and therefore particle interacting with other things, with other particles, with other fields, will be encoded through the potential energy of that interaction. And if you want to relate it to force, well, you relate it like this. This is how potential energy and forces are related. Okay, and you can see that from this definition, potential energy is defined to be minus the work done by the conservative force. A lot more can be said about potential energies, and in the next video, I will continue digesting the intuitive meaning behind potential energies, because as you can see, we need to have some intuitive understanding of potential energies because it's present in the Schrodinger's equation. And before you can solve the quantum problem, you have to have some understanding of the classical version of that problem. So in the next video, I discuss potential energy graphs and how to think about the classical physics by looking at the potential energy graph. It will be very useful for you. Okay, I'll see you in the next video.